Hey folks, Dave Swanson. It's March 4th, 2024, and I actually have a day off, so I'm pretty stoked about it. I've spent a little bit of time on my spreadsheet, and this is not part two of the series that I promised, but this is a really awesome update with my spreadsheet that I'm going to fine tune and throw out there for people to have at some point here, probably pretty soon. So my spreadsheet originally started out as just trying to do the most realistic flight simulation for an ice boulder that I could put together based on the information that I have. So we're going to go over the initial development of the spreadsheet and then the changes that I've made. I will say right now the changes that I made have allowed me to not only calculate what this trajectory of an ice boulder might look like based on its size and velocity and angle of ejection, but it will also allow that information to be used to calculate a final landing point based on a given longitude and latitude of a starting point and a bearing. So then it corrects for the spin of the Earth in that equation. So it's pretty cool, and I hope you guys stick around to see it. It might be a little disjointed because this isn't very well planned, but so my spreadsheet started out with just basically solving kind of this equation right here, which is the equations of flight with drag. So we know these objects were given some initial velocity. That's a vector x and y velocity. We know that it has mass and gravity acts on it, and we know that there's a force of drag. So the force of drag is related to the drag coefficient, the exposed area, and the velocity. So basically what my spreadsheet did initially was to take some initial conditions of velocity, angle, mass, those types of things, and do a very short time step. So we start off initially, say at this point where my cursor is, then we do a very short time step, recalculate using most of these equations here, the distance and velocity change that would experience in a small time step, and then just keep using what you calculated in the step before as the starting point for the next step. So it basically creates like these little dots shown here. This is not my drawing, but it's basically what it does based on the conditions. The main difference that in my spreadsheet that I wanted it to be fairly accurate, because nothing online that I found any calculator did this. It's basically like 10 kilogram projectile at 10 meters per second, and then when you put drag in, it was just a standard drag. It wasn't based on actual air density, anything like that. So in my case, in my spreadsheet, I took air density at different altitudes. So I came up with this equation that allows the air density to be calculated based on y, the altitude up, y, as you see here. Then there's also gravity at different altitudes. So came up with this equation here. Gets a little bit less as you go up in y. And then obviously the half the surface area of a sphere in this case is what would see the drag. But the main thing that's different is that the drag coefficient, they're different from ones online, is that the drag coefficient, CD, that's used all over the place here. You can see in the accelerations and various things. I pulled from this graph that I found from a NASA publication of drag coefficients of spheres versus Mach number. So this goes up to all the way up to Mach 10, and it shows the this is the line that I used, the drag coefficient that they experimentally verified for spheres based on these Mach numbers. So you can see, early in the 1 to 2 Mach range, this goes up really high. down low, it's probably this could be a little bit lower in reality at very, very low, between under 100 meters per second or something like that. But as you get up in these Mach numbers, you can see, and then it kind of levels off at about 0.95, maybe a little bit less. So by applying realistic gravity, realistic air friction, and somewhat realistic drag coefficients, the spreadsheet would more or less accurately, to whatever degree it is, predict the projectile motion that we might see. And we do see time and time again, which in my second part that I present, we're going to go over a bunch of this, but I just thought this was really neat, so I wanted to show you guys. So obviously without drag, we're going to go further and go higher than with drag, and that's what we see. And then the magnitude of the drag is essentially the limiting effect on all of this. So the spreadsheet itself, this is more or less where the computations are done. These tables go real deep, but you can see, or you can't see, the various things that are calculated, the CDs, drag coefficients, acceleration in the x and y, and the distance, and the velocity in x and y, and the vector velocity, and the angle of degree, and then Q, which we discussed in a previous thing that I presented, and that we're going to discuss further. But so in this case, what we're looking at here is my data table for the flight. So this spreadsheet has two parts. It's like we're first going to calculate how far, what's going to go on with the flight. Doesn't matter what direction this is pointed, north, south, east, west. You're going to see, if you get perpendicular to that, you're going to see it go X amount of distance and a certain height. So in this case, the projectile that I entered, you enter data in the green. It's a 60-meter diameter projectile. It has zero spin, which you can add that in the spreadsheet also. It's pretty cool, actually. Initial speed of 4 kilometers per second, launch angle of 45 degrees. So if we did this anywhere on the Earth, shot this off, we would more or less expect it to go a distance of 1,043 kilometers away from the point and reach a maximum altitude of about 260 kilometers. And then that flight time would take 476 seconds. What is that, like 8 minutes or so? So this is like an 8-minute journey. So that's all neat and good, and it's like, wow, that's pretty accurate. If you put in, let's say I put in a 10 meter, just to kind of show you on the graph, 10 meter projectile, basically the less massive, so a smaller projectile, there's actually a mass used in this whole thing. You can see that it really only goes about 14-15 kilometers. It's basically gets slowed down by atmospheric drag and comes in, almost vertical. And you can see here that the impact angle is 90 degrees. So that's this angle from the horizon. So even if we took a 10-meter ice projectile and shot it at 4,000 meters per second, according to this spreadsheet, it would really only go about 14 kilometers. So you really need the bigger projectiles to offset the atmospheric drag. So let's go with a 20-meter diameter projectile. We can see we get this funky shape, but it's still coming in at close to 90 degrees. And what that means is that its forward momentum has basically almost been stopped by air friction. So it loses its arc as it comes up. So let's do 30 meters. Okay, so now we're going out at roughly, hitting 500 kilometers in distance, and it looks more like your standard shape. So we're going to go back to 60. You got the idea. So so after we calculate this, then we basically, in the second part, which I just finished of this spreadsheet, is we assign a launch location, a latitude and longitude, and a bearing to this. So in this case, we tell it to start at 40.6 north, negative 87.0016 west, and the bearing that we're going to shoot this is 180 degrees. So that's perfect south. This bearing is related from north being 0 and the direction being clockwise in degrees. And so we assign that this information. Then from this information, specifically the distance and the time of flight, we can calculate what I'm calling the uncorrected landing position. This would be where this projectile would land if it was shot directly south from this location, and it went that distance. So this is a spherical correction. This is not a spherical calculation. It's not like a flat line type of thing. So let me show you the formula. I've showed this previously, but so this would be if the Earth wasn't rotating, if the Earth was just still, or if the whole surface of the Earth rotated at the same velocity. This is what we would expect. And those are simply these two equations right here. So it's a little tough to see, I know. Latitude 2 is based on the initial latitude, the distance d, the distance traveled, which came from the projectile spreadsheet, and radius of the Earth. So you do this math to get latitude 2. You do this next equation here to get longitude 2. So by taking the initial latitude and longitude as what we entered here, this is where we started, and we use these equations, we get these data right here. Okay, so if you look at that in Google Earth, you see something like this. So this is where you launched it from, directly south from that location. It went that 1,040 kilometers and landed here. So that's where that's where kind of what one would expect, and it would take that 476 seconds, 8 minutes or so to get there. So that's pretty cool. It's not super realistic, but that's what the spreadsheet shows. So then now we know this, hypothetical if the Earth isn't spinning location, but what happens if the Earth is spinning? So I'm going to show you how I've made this is basically the Coriolis correction here, and these are the new latitude and longitude that are calculated with that. And in this case, for this 60-meter diameter projectile, the distance, the offset distance, is always going to be in the longitudinal direction, because the Earth is spinning in the longitudinal direction it's a longitudinal distance as the Earth spins around the axis. So based on the correction, which I'm going to show you, the projectile is in this case going to end up west of that one location by about 21.25 kilometers. So let me show you how I've made these corrections to show where they land. What I determine is there's a formula, which is the cosine of the latitude times 0.4651, gives you the velocity of the surface of the Earth, rotational velocity at any given latitude. So we know the launch location latitude, and we know the landing location latitude. So when you plug these numbers in, and I guess longitudinal velocity may not be the right word. This is rotational velocity, but at the launch location, basically the Earth is spinning 353 meters per second. At that landing location, 1,000 kilometers away, the Earth is actually spinning at 397 meters per second. Let's take a look. So, I penciled that in. These are arrows. I guess you could see they're arrows. Right here, the Earth is spinning 353 meters per second. Down here, it's spinning at 397 meters per second. So we know that this trip took 479 seconds. I think that's what it was. Let's look here. 476 seconds. That's from this table here, 476 seconds. So if we know the velocities at those points and we know the time, we can see the distance that point traveled to the east, towards the east in both cases, in that 476 seconds. So the launch point moved 168 kilometers in that 8 minutes. The landing location moved 189 kilometers in that 476 seconds. So that means that there's actually an offset along the longitudinal line of 21.26 kilometers. And that's the difference that I was saying. So let me show you that in Google Earth here. Okay, let's get rid of these out. So, you understand it's rotating faster. I'm going to get rid of those arrows. So the actual location is there, and I put in a couple points. So if we shot this directly south, the spin of the Earth would offset it about that much. And in fact, that's distance is 21.3 kilometers distance. And I'm going to turn on, just so you kind of get this is really annoying to look at in general, but you're going to see, they basically end up at the same latitude from the point. They're just offset because the Earth is spinning along that line in that direction. So the actual offset is relatively small overall. I mean, that's actually pretty big in a lot of respects. But based on just that simple math of doing the speed differences between those 2 points of Earth, will tell you how much the Earth traveled. And I kind of built this in. Let's see here. Let me get rid of this and let me see. And let me get rid of this. The location, you know what? It didn't save, so sorry about that, folks. But once again, you see that the offset's not that big, really. And what I found interesting, and this kind of is sucky in some respects, in my AutoCAD, I brought in this particular layout, and unfortunately, if I hit escape to get my stuff highlighted properly, let me just send this to back. Okay, so imagine this is that directly south projectile. So this is where we aimed. Let's say that it made a bay here perfectly. If the Earth didn't spin and we looked at this bay, we'd see the long axis pointing directly back to the point that it came from. But basically what happens is if this gets offset, it still keeps this line pointing directly north. Say in this case, it just gets shifted over in the longitude. And so when you look at this, the red line kind of behind this green line is actually pointing back to that location. Let's just review this one more time. So this red line, the second red line on the left, points back to that location. And the and then this other green line on the left is actually the direction that bay will be pointing, because it's just a direct translation to the left. It's still going to have the same orientation. Only thing that happened was it was going to land here, but the Earth rotated underneath it. It lands here. So when you look at the difference between the bay bearing, reverse bearing, this is on the left is where it would likely be pointing. On the right, if we could rotate that bay about 0.73 degrees, it would actually be pointing back to the location that it came from. So really, when you look at these, we're going to look at three examples. They're relatively small corrections in the bearings. It makes a big difference over 1,000 kilometers, distance, 0.73, but it's relatively small orientation. Basically, we just rotate this. Let's say right here. This is not meant to, go in a record book or anything. Here, and let's do negative 0.73. It shows you the difference. Basically, those lines, they're almost lined up. Maybe it's 1 degree, maybe it's more, but it's not that much, really. Maybe there's something that I'm missing in this analysis, but I found that interesting, and we'll look in Google Earth, but here's an example. If that same 60-meter diameter projectile was released at 135 degrees, which is halfway between due east and due south, and we see here this is about a 16 kilometer offset. That's a little bit less at this range, and then we're about up at about the same, more or less same correction in the orientation of the bay. Obviously, this bay, its direction from the point of launch south is 135, so add 180 to that to get that bearing. So they appear to be relatively small corrections in what we would expect in that diameter. And then here's one at 90, and launched at 90 degrees or due east from that launching point. And this is really not to scale. This is less than 2 kilometers. And you might think, well, wait a minute, if this is launched due east, why does this line look like that? I'll show you in Google Earth. But so those are the three examples. Let's go right to Google Earth, and let me put those lines in with the markers. And so we're going to look at this line up here last. But basically, and then let's put in, actual aimed things. So we can see in each case that's 21.26 miles offset. Like I said, about less than a degree change in the expected bearing. This is about 16.5. Let's level that up. You'll see, this is one of the things that kind of got me is, as you rotate around in Google Earth, you kind of get, because, the Earth is round, you kind of, things, when you go from place to place, they don't straighten up. But you can see here that's 16.15 from where you aimed to the actual, with about the same 0.73. And then if you come up and you shot it directly north, you're like, wow, wait a minute. How is, this line directly north? Well, as I said, that's about 1.63, very small. Let's pull this down. Very small offset in the location that you aimed for versus where you landed. And what's interesting here, and I'll have to show you, it took me a little while to kind of figure this out, is this is, pardon the bouncing around, but if you look at this and we zoom in, and let me get this out of the way. Thank you for being patient. Um, at this point on the Earth's surface, um, let me open up this so you can see. So pay attention to the degrees here, okay, as I draw this. I'm going to start here. And this, is rough. You see, it's like if I hover on it really closely, I didn't quite get it in the right spot, but that is 90 degrees heading directly off of that point. And in fact, this other line that I drew we're going to discuss, that's about 86 degrees off of that point. And to be clear, and you can see I'm a little bit off on that right there. So let me click here, clear, and let's zoom in a little closer, and I'll click right on that point and come down. You can see over in the degrees here that when I hover over that initial line, that's like 180. So truly, when you shoot it, when you're at any individual point, really anywhere on the globe, but we're looking at this point, your north, south, east, west is kind of based on flat world. And really, when you have a sphere, it's a little bit different. So if I zoom out, and it's 1,000 kilometers, so it's going to be a while. Okay, if I zoom out, and so we know that this is 90. This bottom line is coming off at 90. But when we put on the grid, what we see is, because of the curvature of the Earth, when you're really looking at these curved, squares that taper, and I forget what the name of it is, a geodesic maybe, but when you're pointing from any one point, if you go directly, in this case, directly east, you're actually shooting from, look at this line right here that goes across. You're shooting from a little bit above that line, and you're kind of ending up on that line. So really, because of the curvature of the Earth, you're actually shooting to a lower latitude. So to compensate for that, so if you're at this point and you wanted to hit exactly west of you, well, I found this kind of interesting. So here's New York. This so we're looking at latitudes now. It's like 40.617, a spot in New York City. Okay, and you're about the same right here at this starting point, 40.617. So you would think if you were firing a projectile, you would fire it exactly east, because that's where it is. But it's really not. And when you look at the great circle that's traced, you'd actually have to fire at like 86 degrees to end up, close to New York. Okay, in the actual direction of New York. This line's only 1,040 kilometers long, so that's just what I started with. So you can see that's kind of an interesting thing that happens, that there is this offset, because if you look at these great distances in that respect, you have to take into account the curvature of the Earth. So I thought that was pretty interesting. And so the crux of this, and so let me turn a lot of this stuff off. so that we can look at this a little bit better. Where is that? Okay, let me do this. Cancel that. Okay, so basically, if we just assume this to be our starting point, which was just random, and we shoot this 60-meter diameter projectile directly south, we'd expect this offset about 21 degrees due to the rotation of the Earth. We'd expect about 16.5 if you did it halfway between the 90 and the 180. And then right at 90, if you just shoot it directly to the east in this case, and it's actually kind of the same with the west but reversed, you get 1.63 kilometers. So the difference in the apparent orientation of the bay, say one that was made here, is very, very small. They're almost, you wouldn't have to correct bays up in this area if they were launched from this point. And this all changes. You move this up here or down, these do change, or longer time of flight. If it's a steeper angle, things like that do change these variables because these offsets are calculated on time and the rotation of the Earth. So it's interesting to see if I pencil in at the different areas. So you can see up here the Earth is spinning at 353 meters per second. Over here where this lands, it's actually 356 meters per second. Down here at the 45-degree point, it's 386, and then down here it's 397. And as I said, that came from this equation here, cosine of the latitude times 0.4651. Then actually to go deeper, to calculate the offset in degrees, you have to take the latitude that you're at, okay, because 1 minute, one degree of longitude at any latitude is this equation here, cosine of the latitude times 111.319 kilometers. So cosine of 0 at the equator, you get 1 for the cosine of the latitude, and you get 1 degree of longitude at that point is 111 kilometers. And then so you just adjust that. So at the landing points, to get the degrees that I offset, so there's a delta, but in this case that we're looking at, we're looking at just the south projectile still, because that's the data that I have plugged in going directly at 180. At the landing latitude 3124, there's 95 kilometers per minute. So you basically take your actual distance that we calculated, divide it by that, and that gives you the degree offset, and then that's in radians, and then you multiply it, or the degree offset rather, in degrees, and you just add that to the what the landing was. So without any spin, anything, this is what we'd expect. With the spin, we calculate the difference, divide by the actual number of degrees, the distance per 1 degree longitude, and do that and correct it that way. So that's how we get the offsets on that. So this is a really I plan on, making this look a little bit nicer. Um, but it's really, I think, can be kind of powerful. And I think a couple things that can be taken away from this is, obviously we're looking at the time of flight and data from my spreadsheet, right? Is that the gospel? No. It's, I think it's pretty cool. It has a lot, to give you a visual feel for it. But I think we can say, unless I'm missing something substantially different than this, is really the Bay offsets from the Coriolis effect are, uh, relatively small. If you turn on the survey, you can kind of see where these are landing, right? And the the offset, let's level this out, is relatively small compared to the band of, let's call it the band of debris, or the where the band of the bays are. So, there would be offset. I could go in for each degree around this and get, actual numbers. So you might have 20 degrees here, you have, less, or 20 kilometer offset here, less up here, so it spans, somewhere in here is about, 16 kilometers. So uh, you could come up with an average, but it's definitely going to be between, 0 and 20 based on this method. But I think really what the nice thing about this is, the spreadsheet and having this, is that you can take these locations and look at these hypothetical trajectories, adjust them, and kind of get a feel for uh, what's going on. Unfortunately, we don't know the crater dynamics of the bays, right? Um, any type of real analysis into these elliptical craters, it takes a lot of knowledge of what the soil is, what to expect, why are they all elliptical. Yeah, conical sections do that. Also, kind of exploding, weakened materials that could hit with forward momentum could also make, craters like that. Um, so far, my spreadsheet can't just take a random Carolina Bay and uh, back calculate back to here, because for my spreadsheet to work, you need to know the size of the ice boulder. You need to know the trajectory. You could plug some stuff in and maybe back calculate. But what I think it can say is, in general, let's just, and I didn't do this to be close to bays, but so, we look at some of these orientations out here. Boy, that one's almost right along there. And we can say, most of these that would, if they came from the area that I'm showing, most of these would have a adjustment of about 1 degree clockwise, averagely, or a little bit less, 0.75. So you could come in and say, okay, this one's got whatever this bearing is, let's adjust it, and then let's adjust this, and then let's adjust that, and maybe applied across everything would give a little, point a little better to where these actually came from. But what we're actually seeing with with the bays is that there's big streams of debris that you'd expect as these big curtains of debris came in. So I'm just kind of rambling on right now. So as I said, the spreadsheet now can be a lot more powerful and could estimate not only kind of what the flight path would look like for some hypothetical boulder that we plug in the data on. It would also, you can give it a starting point and bearing. Then you can essentially end up with what you think might be the final bearing and offset distance based on the latitude and longitude and bearing that it was launched on. One of the interesting things also about this spreadsheet, and I'm maybe give you a little tease of things. So this data, this graph is based on, again, that 60-meter diameter at 4,000 meters per second, 45-degree launch. Okay, what we're going to end up doing in these other, can I get that out of there? No, I guess I can't. When I continue is we're going to go over this thing called the stagnation temperature, which is used to estimate what we might see for this hypothetical boulder. Now, in this case, 4,000 meters per second, 45-degree launch angle. I've plotted three different variables here. Here's the elevation, Y only, is the yellow. You read that off of this side in meters. So you read on that side. Q, which is the pressure, aerodynamic pressure, is measured off of this size, and that's in pascals. So that's 9 megapascals, 10, 11, 12, 7, 1. And then the Mach number, which is the sea level Mach number, is the green, and that's measured over here such that you just kind of ignore the zeros. I just ramped it up by that million or whatever. So, right around here, you're almost Mach 9. Right here, you're between Mach 6 and 7. So on this hypothetical projectile, we're going to see these, huge aerodynamic forces at 10 megapascals for roughly the first, the first 12, 13 seconds. We're up in high Q range. When we hit about in elevation now, about 50 kilometers, and you read down about less than 20 seconds into the flight, the Q goes down to almost nothing. So there's like zero almost aerodynamic forces until it starts to re-enter. So you see here, this is the peak. Re-enters like this. So from that point on, you start to get more into the denser atmosphere, and then the Q, the black line, goes back up to a max of around 3 megapascals as it's re-entering. Based on the stagnation temperature, we would expect, and maybe I should go over it. This is getting pretty long. Stagnation temperature, there's a graph that tells you kind of what temperature you would expect the aerodynamic drag to present based on elevation and speed. And so we'll go over that. So, but I guess, from that document there, we would expect, if this just did experience aerodynamic drag on the way out of the atmosphere, this is on the way out, we'd expect at least 5,500 Fahrenheit or above for at least 12 seconds of that. And then coming back in, we'd expect about 13 seconds of 35 to 4,500 Fahrenheit. You might be asking why this 12 seconds is different than is spread different than this 13, and this is just the iterative approach that I took, traveling a lot more distance in shorter time. just creates more data points in the one area versus the other. So, but you can see that, still when we're re-entering, at this point we're at, this point of this green peak. If you come down to the yellow line and then read across, you're at like 40 kilometers, maybe 50. So once you hit that 40-50 kilometer range, this air friction just really ramps up, and but you're still, you're hitting the ground basically still at like Mach 6.5. And you're going fast, and so that's why I use those equations of drag coefficients for high Mach numbers, but they still didn't really even go up to the Mach 11 and stuff. So that's kind of the data that you can get out of the spreadsheet, just related to what you might experience with an actual projectile launch. Obviously, it doesn't talk about the strength of materials or anything like that. My previous Max Q story was, or a video was probably not the full story, but some other data that I'm looking at, some other papers, some other modeling that might kind of change this for any given projectile and make this section, this really super high stress, high force section, which would obviously be very hard on ice or any projectile. It might make this look less like this. And if in fact a lot of debris was actually entrained in a moving atmosphere that was moving along with the debris at such a scale, we would see a lot less of this Q in this area here. And it, maybe could resemble more of this area here. So that's pretty much this presentation. The spreadsheet does some cool things now. Made a corrections. If you have any questions, or if you found an error, if I'm looking at something wrong or analyzing something wrong, let me know. I'd appreciate it. Thanks. Take care.